Today we'll talk about maximum and minimum. Right, a nice function to think about for maximum and minimum is the following one. Let's start with a very simple one. Y equals to x squared minus 1. What's the graph of this function? It's a parabola. Y equal to x squared is this thing. What does this minus 1 do? Shifts everything one down, right? Everything down by 1, so it's going to be this graph. Now, it's not this one that we want to look at. It's actually the one with the absolute value. What happens if you put an absolute value? What does absolute values do? What does this function do? If it's negative, it makes positive. If it's positive, it doesn't do anything. It stays as it is. Okay. So it will compute this value, and if it's positive, then it's not going to do anything. But if this value becomes negative, it's going to make it positive. So let's think about what will happen to the graph. Okay, so for example, this point. Is the y positive here?
Yeah.
It's positive, right? Because y is the height, right? Is this positive?
Yes.
How about here?
Yes.
It's still positive. It's above the x-axis. Then this value will be positive. Now, how about this one?
No.
This is negative. This one is when you have below the x-axis, so it's negative. What would the absolute value do in this case? You will bring it up as positive. So what you're going to get is everything that's below the x-axis will be brought up like this. So that's the function that we want to look at. And for this function, we want to talk about maximum and minimum. Right? Of course, this function doesn't have a maximum because it can go up forever. Right? What's the minimum of this function? The minimum value of this function occurs here and here. That's at zeros. Okay. Now, here, this point here is not a maximum, but it can be considered as a maximum if you only consider this portion of the graph. So it has a name. This point here has a name, which is called relative maximum, meaning that it's bigger than the nearby points. Okay. Another name that some people use is local maximum. That's another way people call this point. But we will try to stick to relative maximum. If by chance, if you are working on your homework or in some other question set, or you're watching some YouTube videos and it says local maximum, just understand it as relative maximum. Okay. Now, this point here is also smaller than the nearby points, right? So you can say that this is a relative minimum. But it's also a global minimum or absolute minimum. Absolute minimum means it's minimum even if you consider the entire function. It's the smallest value out of the entire function. Some people use the word global minimum. So these are interchangeable words. Instead of saying absolute minimum, you can say global minimum. This one doesn't have an absolute maximum. But you could, if you restrict this function from some interval, inside that interval, if you restrict the domain to some interval, then inside the domain you may have a highest point, and that will be called the absolute maximum or global maximum. Okay. All right. Now, the question I want to think about is for this function. When does relative extrema occur? By extrema, I'm talking about a maximum or a minimum. Do you know what's the singular of extrema? Extremum, right? This is a plural. Extrema is a plural. Just like minimum is actually a singular, and the plural of minimum is minima. So you can, if you have many relative minimums, well, that's incorrect to say many relative minimums. That's incorrect. You have to say many relative minima. Okay? So when does relative extrema occur? Let's look at this graph and see when these points occur. I guess the easiest place to think about is right here. What's so special about this point at the middle? It's a point where first of all, it's a turning point. That's how some people call it. Another name for these relative maximum or relative minimum is it's a turning point. And if you think about the tangent line, what's so special about the tangent line at this point?
The slope is 0.
The slope is 0. It has a horizontal tangent. So either slope is 0, or what else happens? Like this point. Do you have a tangent line here? It's a cusp, right? It turns sharply. So it really doesn't have a tangent line defined at these points. So you know that either slope is 0 or not differential. So that happens for points where you have a relative extrema. And because of that, I'm going to define a new word here, definition. The definition is a critical number say x equal to a is the x value where f prime of a is 0, or f prime a means slope is 0 because the derivative has the information of the slope derivative has the information of the slope of the tangent line, right? Or what? What corresponds to this? F prime of a does not exist. That's what a critical number is. Now, why would we need such a definition? We need such a definition because theorem of relative extremum has x value such that f prime of a is 0 or f prime of a does not exist, i.e. a critical point. So relative extremum will always have the x value a critical point. Not critical point, critical number. So a thing about extremum and a critical number that you need to know is that extremums are actually points. Okay? It's a point on the graph, which means it has both x and y coordinates. Whereas critical number is a number because there's only an x value. It's just the value of x when either this happens or that happens. Now, one thing that you could misunderstand in this definition is that you may think the critical number will always give you a relative extremum, which is not true. So think about the following example. If you have y equals to cube root of x, the graph has a point where you can't differentiate right here. Okay? The graph looks like that. And if you try to evaluate y prime at x equal to 0, see what happens. This is x to the 1/3 power, so 1/3 comes in front. Subtract 1 off 1/3, that's negative 2/3, which is same as 1 over 3 times x to the 2/3 power because of the negative exponent. And when you evaluate this at x equal to 0, you get 1 over 3 times 0 to something. So this is 0. This is 1 over 0, which is undefined, right? This does not exist. So this says that x equal to 0 is a critical point. Now let me ask, is this point a relative extremum? It's not. It's neither a relative maximum or minimum, because if you just take the nearby portion of the graph, the right side is higher than this one, the left side is lower than this one. So it has, no matter how small you take the neighborhood, you always have some portion that's bigger and some portion that's smaller. So it's neither a relative maximum nor relative minimum. Therefore, being a critical point does not guarantee that you have a relative extremum. However, the opposite is true. If you have a relative extremum, then it must happen at a critical number. Okay? So this gives us a strategy for finding maximum minimum, or at least a relative maximum, relative minimum. The strategy for finding relative maximum, relative minimum is first look for all the critical numbers. And that's not so bad, because you just have to differentiate z equal to 0 and also figure out when the derivative is not defined. And then for those values, you just have to check if that point is relative maximum, relative min. So the critical number is a great way to reduce the points that you have to consider. Okay? If we didn't know about the critical numbers, then anything could be a suspect, right? But by only looking at critical numbers, that reduces the number of suspects where we can really find the true relative max or relative min.